Okay, 4.7 isn't really anything new. Just involves putting it all together in larger problems. So in that case, we'll have forces that are um, both have friction, tension, parallel force, weight force, perpendicular force, and putting those all into single problems that we could solve. Okay, so it's combination problems. Combination problems, but still making use of the first law of no net force. Sum of the forces equals zero. So overall, we have no acceleration, um, but we still have problems for it. So okay, so let's take a table. So we'll just do a couple examples here, and then many more in class. So on this table is a 5 kilogram block, and the mu value between the block and the table is 0.5. And then goes off to a pulley to another mast that's hanging down here, and we'll connect it with um, rope, string, or whatever. And so that hangs down to that one, and then that's connected to a wall over here, like that. We'll just use these ticks for a wall. Those are connected, and that's connected at an angle of 20 degrees here and 70 degrees there. And we're interested to know, to be able to solve for this unknown mass. Okay? Alrighty, so to do that, we have to set up some free body diagrams to find which forces are equal, set them equal to each other, be able to solve for it. So if we take the first block up here, its free body diagram, well, we have its perpendicular balanced by the weight force. We have friction force, and we have the tension force, like that. And the friction force equals the tension force, and the weight force equals the perpendicular force. Now, for the mass, the mass over here, this one, well, we have the weight force down, and that's being balanced by two tension forces, Ft1 and Ft2, like that. Now let's set this up to see what we can get here. Well, from the first one, we know that Ft from the sum of the forces equals 0 equals Fs. And that tension is also Ft1, since it connects in a rope around to that. So Ff would be mu times F perpendicular, which is, since it's flat, mg. So we know what we can calculate it right off the bat because we know what mu is. It's 0.5. We know what F perpendicular is because it's just mg, and our mass is 5 kilograms times 10 meters per second squared. So we end up with 0.5 times 5 times 10, or 25 newtons. So now we know that over here, that this is equal to 25 newtons. So right off the bat, we're going to take that Ft1 over there, where we know it's 25 newtons and 20 degrees, And we're going to find, I'm going to simplify the notation a bit and find T1x and T1y. The components of that, which would just be 25 newtons times the cosine of 20 degrees, standard, right? And this one would be 25 newtons times the sine of 20 degrees. 25 sine 20 is 8.55 newtons. Is our T1y, and our T1x would be 25 cosine 20, or 23.5 newtons. Okay, so we can get that right off the bat. Well, right off the bat, we did considerable amount of work to get it. Now, if we look here, we also could take this FT2 here, and it breaks into, simplifying it a bit, T2x, T2y, and I'm just leaving out the F for simplify it so there's not tons of, FT2y, which is a little bit extreme. Now the thing about this is that because the block in the x direction is not moving, we know the sum of the forces for this hanging mass right here in the x direction must equal 0. So T1x must equal T2x. And we found T1x. It was 23.5 newtons, so we know what T2x is as well. And then that, we can come over and plug it in and solve for the rest, because now we take this and we have FT2, but now we know that that part there is 23.5. We know that's 70 degrees, so we can get T2y now and FT2. Let's take our standard component in the x component direction to find FT2. So T2x equals FT2 cosine of theta. But T2x is 23.5 newtons. FT2 cosine of 70 degrees. So FT2 will equal 23.5 divided by the cosine of 70, or 68.7 newtons. Now once we have that, we can do our standard y to find T2y, which would just be 68.7 newtons times the sine of 70 degrees. And T2y would be 68.7 times sine of 70, or 64.56 newtons. Okay. So now the other thing we have for this is we want to get the mass eventually of that hanging mass. But we also know that from our sum of the forces in the y direction equals 0, that the FG down for that is going to equal the two y's going up, the T1y and the T2y. Now T1y is 8.55 newtons plus T2y, which was 64.56 newtons. So we get Fg equals 73.1 newtons. Now from that, it's also equal to big M times G. G is 10, so big M equals 7.31 kilograms, and we solved that problem. So it's a bit tricky, but as we go through more and more of them, it will become more clear. And I know I went through that quickly, but you could always go back through it as well. Okay, next problem. One more we'll do. In this case, we have a table, and on the table, we have a ramp. And on the ramp, we have a block. And that block goes around a pulley to another block hanging off. And the system is in equilibrium. Okay? So, if this block, we want to know the coefficient of friction of it, and we know that this is 8 kilograms, okay, and this is 12 kilograms here. We're wondering what mu is, and this angle of the ramp is 30 degrees. Well, if we set up some free body diagrams, for the one hanging, we'll make that red. We have a tension up and a weight Fg down, weight force down. And because the sum of the forces equals 0, Ft equals Fg, which is 120 newtons. Now for the block over here, make that blue, we have F perpendicular, Fg, we have the F parallel, part of Fg in the plane, and we also have friction, which is going in that same direction, so we'll put that here as well. Friction, force, keeping the block from sliding up, because if this is allowed to go, the 12 kilogram, well, that would be great enough to pull that up against because the full weight force of an 8 kilogram is 80 newtons. So if it was frictionless, it would go 120 newtons would pull whatever component of that 80 newtons is in the plane. So we know that friction must act against that direction down the plane. Okay, so that's a little tricky, but we can see that. So in this case, we also have tension up like that. Okay, and if we do the sum of the forces equals 0, Ft must equal F parallel plus Ff. Now we know what Ft is. It's 120 newtons. F parallel is Fg sine theta, and the friction is mu Fg cosine theta. Well, Fg is 80, so 120 newtons equals 80 newtons times the sine of 30 degrees plus mu times 80 newtons times the cosine of 30 degrees. 80 sine 30 is 40 plus mu times 80 cosine 30 is 69.3. So subtract the 40 over. You have 80 newtons, right? Yes. Equals mu times 69.3 newtons. Divide by 80 by 69.3, we get 1.15 for our mu. And that solves the problem. We'll do some more later. And that's the end of topic 4. Topic 5, we'll start adding some net force second life with mass times acceleration. So we'll have a net force.